with our two types of reactions. We've already talked briefly about chemical reactions. And so with chemical reactions, this is going to be the rearrangement of atoms. So what's going to happen is those atoms and those compounds, they're going to break apart from one another if they're attached, and they're going to rearrange. So whenever you hear anything about rearranging of atoms, we're talking about a chemical reaction. What we'll talk about is the difference here between chemical reactions and our nuclear reactions.
Thank you, sir.
You're welcome. So, big thing here, I didn't have you write anything down. In a chemical reaction, the nucleus, the number of protons and neutrons in that atom, is going to stay the same. Let you get caught up, Bethany. Just a question for everybody here. If you change the number of protons, what have you done? Yeah, you're now working with a different element. So if we don't change anything, all of the elements are the same, and you can see that through the chemical equation here. Good. All right, anybody else need it? All right, so on the flip side here, and this is what we're going to talk about today, is nuclear reactions. So this is when we're going to change pieces and parts of our nucleus. So bits and pieces of the nucleus is going to either decay or stuff's going to be added to it to produce these nuclear equations, or what we'll have as nuclear equations. So radioactivity is when substances are going to emit that radiation. And radiation you can think of as energy in terms of rays and particles. So essentially you're having energy leave the nucleus. Now there's a little bit more to it than that, but that's what I want to keep it simplified here. Basically something's happening in the nucleus. We're having stuff leave it, and so that's causing a different substance to be produced. So in these equations, and we'll talk about it here in a second, in these equations right here, they are going to have one substance turn into another substance. And it's all throughout that change that happens in the nucleus. Questions on any of this here? Anybody still need it? All right, we'll keep moving on here. So we get into two types of radioactivity. Number one is decay. So this is when you have an unstable nucleus deteriorate into something else. Basically what happens here is there are too many neutrons to protons, and so that nucleus, remember, is really, really dense, all of a sudden says, hey, I can't handle it. I have to give off energy so I'm more stable. And so when that happens, there's two things that occur. One, you get this energy in the terms of these particles, which think of the particles as rays and energy leaving that nucleus. And then the other thing is that you produce that new substance because items have left that nucleus. So what we're going to talk about is three main types of decay once we introduce our nuclear equations through that. So anybody have questions? Need it? All right, moving on here. Again, going through the types of nuclear decay. We start out here with alpha radiations, and you can't see that, can you? That is not helpful, is it? Let me. All right, so it says it's radiations that's deflected towards negatively charged plate. Basically, what this means is that it's going to have a positive charge, specifically a positive 2 charge. That's the big takeaway from us. Now, it's been noted that we use this as, or it is a helium nucleus. The one thing to remember if you write it like this, it doesn't have those electrons. It's just the nucleus that would be leaving the atom. Now, our example here of alpha radiation is going to be the decay of radium-226. And so, let me make sure. Oh, I talk about this on the next page, so I'll save it for the next page. But we'll go through how we specifically write a nuclear equation. Any questions on this? Anybody need it? All right, let's move on here. All right, so nuclear equations. Like I said, this comes into play here. But what you have to do, we still have to abide by that law of conservation of mass and matter. So in a nuclear equation, we still have to account for where everything went. So this means that the number of protons has to equal itself on the left and right hand side. The number of or the mass number also has to equal each other. So I'll let you write this down and then we'll go through this example. All right, anybody still writing? All right, so how we write these equations is as follows. We take the element symbol. So the element symbol for radium is what? Yeah, Brecken.
RA.
RA, all right? Then we write it in that element symbol notation. So we have RA. In the upper left-hand corner, we write that mass number, which is indicated here as radium-226. So we write 226. And then we write the atomic number for radium in the lower left, which what is that atomic number? Brecken.
88.
88. So we put 88 right there. And then we have a decay. So whenever you see decay, that means it emits this particular particle. What that means for us is if it emits, it's going to be on the right-hand side of the equation. So it emits an alpha particle. As you can see from this chart or on the previous page of notes, an alpha particle is written like this. Now, you may use the symbol for that alpha particle that was shown on the previous page, or you can use that HE. I like to do it because I can't draw the goofy symbol for that alpha. Now, what has to happen is we have to have the same atomic mass on our left and right-hand side. So we ask ourselves, 226 has to equal 4 plus something. So essentially what we're solving for is 4 plus what equals 226? 222. All right, so this becomes our mass, and we start out by writing that. And then we have to conserve our number of protons. So again, 2 plus something equals 88. 86. Now, this is golden here because this is not only our atomic number, but it's the number of protons, which tells us here, what element are we now working with?
Radon.
Radon. How did you find that?
86.
It's atomic number 86. So that means that symbol is written there as well. Questions over that? Major thing here is atomic masses added together have to equal, left and right hand sides have to be equal, and so do the number of protons. Any questions on that? All right, we will go through the examples with our other types of radiation here. All right, so beta radiation, just another form of radiation. They call it equivalent to an electron because it has no mass and it has a charge of -1. Now, in reality, there isn't really an electron leaving the nucleus because electrons, they don't exist there. It's a type of energy that is very, very similar to that of an electron. But for us, hey, equal to an electron. Now, going through this example here, we have carbon-14, and it says, hey, it decays via beta radiation. Bless you. So we start out by writing carbon-14 in that symbol notation, and we need the number of protons. So for carbon, what's the number of protons that we have?
6.
6, that's the atomic number. It decays via beta radiation. So the symbol for beta radiation is exactly seen here up above. You have 0, -1 with that Greek symbol of beta. Then we ask ourselves, okay, 0 plus what equals 14?
14.
14, all right, so that maintains our mass number there of 14. -1 plus what equals 6?
7.
Too easy, right? Atomic number 7 is what element?
Nitrogen.
All right, too easy. Questions on that? Again, atomic mass has to equal, number of protons has to be equal. Anybody need this? All right, so our last type of radiation, and our last section, our last slide of notes for this particular section is gamma radiation. Now, gamma radiation has no mass, no charge, so I want to say it doesn't affect the number of protons, and it doesn't affect the number of the mass number, but it does have energy. Okay, so again, this is a very, very highly energetic particle that leaves the nucleus as well. So on this problem here, I don't have enough room to write it, so I'll write this example up above. But if we have uranium-238 decaying via alpha decay with these accompanying gamma rays, we would have the following. We would have U for uranium-238. What is uranium's atomic number?
92.
92. The first thing that happens, or that we need to identify, is that it goes through alpha decay. So alpha decay would be written how? 4,2 helium. Then we have to decide, well, what did that decay to? So 4 plus what equals 238? 234. 2 plus what equals 92? 90. What element has the atomic number of 90? Thorium, Th, right? Then we have to worry about this gamma rays, all right? So gamma rays is not going to affect any of our protons and our atomic mass, but it has to be written because it says, hey, gamma rays accompany this. So we would just tack on 0, 0, and this upside down Y ribbon looking idea. So any questions on that? Okay.